This lecture is going to focus on optimization. Optimization is a big deal. Probably optimization and the fundamental theorem of calculus are the two biggest ideas of calculus. Optimization is the classic find the maximum minimum, optimize performance, minimize friction, maximize profits. It extends to everything. It's a big deal. Unfortunately, we're not going to spend a lot of time on it essentially this lecture, but it's pretty straightforward, and again, as I said, it's a very big deal. You'll do basically in your career optimization, fundamental theorem of calculus are your two biggest tools and most powerful. So let's look at this a little more carefully. Now, I've been introducing the global optimization on closed and bounded intervals since something like, I don't know, one of the earliest lectures. So I haven't really jumped into problems because we don't have all the pieces in place. So today we'll finish that up. So what I want to do is introduce this idea of critical points. Now again, think about this. In all of calculus, you have one idea called the critical point. Right? One idea. It doesn't mean 50 things. You have one idea that says they're critical. What would be critical? Why would they be critical? Because they're necessary for this big theorem, the optimization theorem. So what is a critical point and why do we care? First thing is I have a function, right? You always have to be talking about functions in calculus, and I want that function to be differentiable. Because again, we introduced this idea earlier. If you say the function is continuous on the closed and bounded interval, you can say there's a maximum or minimum. You can't begin to say where they occur unless you have differentiability. So again, if you want more, you have to pay me more. I need more smoothness if I want to know their location. Okay, and again, we talked about this earlier, but we're going to introduce it in terms of the notation. So a critical point, right, a point that is critical is a point, right, it's a point, right, C represents a number, and again, why do you call it C? C stands for, I don't know, critical point, right? So there's a point C, and the Y value is f of C, right? So that this is the C, x equals C, is either a zero of the derivative or the derivative is undefined there. Now to be honest, there's some flexibility here. You can either say C is a zero of the derivative, or you can say C is either a zero of the derivative or where the derivative is undefined. Again, different authors take different approaches. For me, I'm just going to say it's either the zero of the derivative or it's where the derivative is undefined at that x value. Right? The x is a box. What goes in the box is this number C, the critical point. And the value x, the number that goes in this box, is called the actual critical number. Again, we tend to blur this. We call the point the critical number. We call the number itself the critical point. Technically, this is the critical number, and this C, f of C, the xy value, is the critical point, okay? But again, it's not worth getting excited about. Now think about it. Why is it important? What happens? What is the reason why this point is important? And why do we need differentiability, right? Why is this important? Well, where the derivative, with the critical number, what happens? We said that the derivative is zero, but by definition, the derivative is the slope of the tangent line, right? Change in y, change in x. See, this is why, again, you have to have these things automatic in your toolbox. When you say derivative, it's just a function. When you say derivative at a point, it's a slope of a tangent line. That's the chain of thought you should be training yourself to have. So I know the slope of the tangent line is zero at this critical number or at this critical point. Why is that useful? Again, draw a picture. Think about what this means. You're looking for optimization, right? Maximums and minimums. So what happens when the slope of the tangent line is zero? Again, sketch this stuff on the back of an envelope. That's how we actually do math, right? The tangent line is horizontal there. So what does that mean? Well, here's a picture. Here's one picture. Here's one possible scenario. We can see where the tangent line is horizontal. This is a minimum value. And of course, you could flip it over and it would be a maximum value. And that's good. That's really good. So that's why we need differentiability. Differentiability gives me slope of the tangent line. And remember, the function looks like the tangent line locally. And you can see in this scenario that we actually have a minimum or flip it over a maximum. That's optimization. But what's the problem here? What else could go wrong? Here's a picture. This is, for example, x cubed, f of x equals x cubed. Here's a picture where the tangent line is horizontal. But you can see that's clearly not a maximum or minimum. So what we can say from this, just sketching, is that maximum minimums occur at critical points, right? At critical points. They're critical points, but that's not enough, right? It's not enough, right? You can also have false readings there, if you will, right? You can have a critical point, but not a maximum. So we know that they're going to occur in the interior, in the inside, right? In the inside of the critical points. So this is what we learned. And again, the value of this theorem, global optimization on a closed and bounded interval. Of course, for any one-dimensional problem, who cares? You just draw the picture on a graphing calculator, or on the web, graphing calculator on the web. I mean, it's no big deal. But the point is, this extends to any number of finite dimensions. And again, it's not just 3 dimensions in time. I mean, if you have inventories, you have all your products and so forth. So this is the kind of result that extends, and you'll do this in Calc 3. It extends to more than one dimension. And that's why, again, everything you think of math is, it's all pain, it's all suffering. No, those are algebraic gimmicks, tricks, memorizing formulas. We try to use, when you actually are using calculus, you use simple, powerful tools. Global optimization theorem on a closed and bounded interval. Fundamental theorem of calculus. Not the way you know it, the way it really is. So this is the issue. This is a very, very powerful and easy to use theorem. So we know that our global max and mins are going to occur at critical points. But being a critical point is not enough, right? It can give us a false reading. All right, so let's look at the theorem again. We've been looking at this again from the beginning. If I only have continuity on the closed and bounded interval, right, up to and including the walls, right, I can say that there exists a global maximum value and a global minimum value, right? So the temperature in the room, there is a global maximum and there is a global minimum somewhere in the room or on the wall. I know that. Then you ask, well, where is it? I don't know. Can you tell me how to find it? No, of course not. But if I add smoothness, right? So C is a critical number, right? C is a critical number of this function, meaning the derivative is either 0 there at x equals C, or that the derivative is undefined there. So if the function now is continuous, and, right, intersection is and, differentiable everywhere except for that critical point, right? Because it may be undefined there, right? It may be undefined there, so the derivative may be undefined there. Now the function is defined there, right? The function is defined there, but the derivative may be undefined there, right? Think of the function f of x equals square root of x. See that's it's obviously going to be undefined, and the derivative is 0. All right. Anyway, then the global maximum or minimum occurs either at the endpoints of the interval, right, on the wall, or at a critical number, right, or at a critical number that gives us the interior of the function. So I'm either going to look at the interior, right, I'm going to look at the interior. It's either going to occur where the tangent line is horizontal in the interior, or it can be on the ends. I don't know exactly where it is, but it's going to be in those locations. Oh, okay, you can say that's not perfect, doesn't tell me exactly. But there's only a couple of these locations. Just make a table and check. The biggest one is the maximum. The smallest one is the minimum. And all you have to do is take the derivative. Use a derivative calculator. Take the derivative. Find out where it's 0. Find out where it's undefined. Bingo, done. Very straightforward. Very powerful, because this extends to any number of finite dimensions. I mean, this is huge. So here's a simple problem. Determine a global maximum value of f on the interval minus 1, 2. Now, of course, this is a completely artificial problem, but okay, we still test a procedure. And again, it's not just ad hoc. You just don't make it up every time you do a problem, right? It's a very defined procedure, and it's very, very easy to use in any dimension. So again, notice my interval is closed and bounded. minus 1, including minus 1, to 2, including 2. So we have the interior of the room and the walls included in this. Right? Again, this is a polynomial, so we know it's going to be continuous here. Right? We know it's going to be continuous everywhere here. All right, so we know from the global optimization theorem that the global maximum or minimum occurs at either the endpoints, right, or at the critical points. So it's either going to occur on the left, on the right, or somewhere in the middle. If it's in the middle, it's going to occur at a critical point. So, okay. Again, here's the function, right? I always like to set this up. Notice they tell us in fact, the domain is minus 1, 2, right? I mean, the polynomial is defined everywhere, but it's only defined on the interval. So again, think about it as the temperature in a room or the conditions in a room. I don't really care what goes on outside of the room. I'm just talking about the room itself, right? So in principle, you have a temperature everywhere in the world. I'm just talking about the room. All right. So we want to find the critical numbers, right? And again, just recall, what are the critical numbers? Well, the critical point is the point such that the critical number, the derivative, is either 0 or undefined, right? So I'm really looking for the critical numbers of f are the zeros of fx, right? The zeros of the derivative, or undefined on the derivative. So I need the derivative, right? I need the derivative, right? So here's the derivative, right? So just at some point, take the derivative. And again, I didn't put in all the steps. I mean, we've spent a lot of time taking derivatives, whatever. I mean, this is simple. You can do it in your head. Again, I'm not trying to make every problem a monster. Just take the derivative, right? Use a derivative calculator, whatever at this point. It shouldn't be difficult. Now that I have the derivative, right, what do I want? I want to know where its zeros are and where it's undefined. So again, at this point, I'm not looking at this as being any. This is just simply a function. Just simply a function. Tell me where this function is 0. Tell me where this function is undefined, right? So again, here's the function just again on a different slide. Find the zeros. Find the zeros. So a 0 is where, I don't know, why would you call it a 0? It's where y equals 0, right? I mean, it's where the function equals 0. What else would you call it? 12? It's a 0. Call it potted plant? It's a 0. So, okay, it's set in a function. This is the definition of a function, right? That's the rule. And we just factor this, right? It's a polynomial. We can always factor it. Again, it might not be pretty, but we always can factor it. So I'm going to factor out 12x squared, right? Just distributed property. And again, we all have to practice algebra. I'm just going to put in the properties. I'm not, again, if you don't have any problems with this, it's no big deal. Remember, we always have, right, a is 12 is not 0, so I'm just going to get rid of the 12, right? It just divide by 12. Here I have, again, the classic, a times b equals 0 means a is 0 or b is 0, right? Again, there has to be a reason why you can do something, right? There has to be a reason. Again, there are very few rules that we actually use frequently. A times b equals 0 means a is 0, b is 0, right? A is 0 or b is 0, right? Again, this is x times x. So again, you have a equals 0, b is 0, right? So you have x is 0 and or x is 0, right? This is just a repeat. And or x minus 1 is 0. And so you have x equals 0 and x equals 1. Now, the fact that this happens twice has some implication, but again, it's no sense making a big deal. But that's technically how it works. It's not a guess. It's not a random process. There is math behind this. We tend to just shortcut this, but again, the more steps you leave out, the higher the probability you're going to make a mistake. And also, you should know the reasons. If you skip them, that's fine, but you should still know what they are. Okay, so we know where the zeros are, right? Now we need to know, so we found the zeros, and we need to now know where this function, the derivative, is undefined, right? So where is it undefined? Well, it's a polynomial. It's defined everywhere. It's never undefined. Generally speaking, it's going to be undefined where it's a divided by b equals 0. Right? Generally, that's the case. I mean, of course, square roots are undefined for negative numbers if you're talking about real numbers. Logarithms are only defined for positives. But again, we're talking about points. Generally, it's going to be a divided by b. So we're defined everywhere. Now we want to find the critical numbers, right? The critical numbers. Well, the critical numbers are, by definition, again, it's not a random process. It's not because I say so or some mystic principle. The zeros are x equals 0 and x equals 1. And if we had any places where we were undefined, we just tack that onto the list. So these are the critical numbers of our function, right? They're critical numbers. So let's apply the global optimization theorem. It's very, very easy, and it generalizes to higher dimensions. F is a polynomial, so it's continuous everywhere, including the closed and bounded interval. And it's in fact differentiable everywhere in the interval, right? Here's our function. Here's our function, and this is the main. All right, so we know the theorem applies here. So how do you proceed? I'm simply going to make a table. I mean, it's this simple. It's always this simple. And again, people have other ways. Well, you do this, that, you're doing this. No matter how you're doing it, this is how you're doing it. I list my endpoints. They're on the ends. Critical points occur in the interior, right? So these are my critical points, and you see these are my endpoints are minus 1 and 2. Then we just evaluate the value of the function there. I mean, just plug in. You just plug in. And I'm thinking the biggest is the maximum, the smallest is the minimum, and bingo, you're done. Right? So that's the global maximum. It occurs when x equals 2, right? When x equals 2 is where it occurs. And the maximum is 16. And you know that for a fact because of the global optimization theorem on closed and bounded intervals. It's not my opinion. It's not just a good guess. It's not because I said so. It's a fact. The theorem proves it's a fact. So although I only checked 4 points, I know for a fact that that's the maximum. And if I wanted the minimum, it would be minus 1, and it would occur at x equals 1. And again, you're going to learn to generalize this in Calc 3 to multiple dimensions. That we use this, it's a powerful tool because it's easy to use. And in fact, it generalizes. Now, in one dimension, I mean, of course, this is going after a fly with dynamite. I mean, this is, you just draw the picture. I'm not so naive to think we have to make every problem a mountain. But again, the value of this is it does generalize to higher dimensions. So you can see the maximum occurs at x equals 2. The minimum occurs when x equals minus 1. Notice the tangent line is flat here, right? So this is a critical point, 0, 0. But you see, it's a false reading, right? It's not a global max. It's not a max of any kind or a minimum. It's a false reading. So we can ignore that. And you see, this one is would be a local max. I mean, it's bigger, its neighborhood would only be on this side. But again, I'm not looking for the local max. I'm looking for the global max, right? Because its domain is only from minus 1 to 2. And that's it. I mean, I know for a fact, it's not a guess, it's just not a hunch, that that's the maximum, and that's going to be, I didn't ask for it, but a minimum. And that's it. I mean, this is the standard process. It's not hard to do, and yet it's extraordinarily powerful. So here's another problem. Why don't you give it a shot? Pause the video, follow the exact same steps, and you'll come up with the exact same answer. Okay, so pause the video, jump in there, give it a try, and you'll see this is not difficult to do. Okay, good luck. Stop. I'm going to start at the second. Okay, let me jump in. I think, yeah, again, it's exactly the same procedure. I don't need to reinvent the wheel. And when you go to higher dimensional calculus, it's the exact, well, there's little nuance, but it's essentially the same. So again, here's my rule. Here's my set, right? And my range is, again, it's going to be contained in the real numbers. Big deal. Mine is 1 to 3. It's closed and bounded, right? It includes the endpoints. It's bounded. So again, what are the critical numbers? They're where the derivative, right? The function derived from f, the derivative is either 0 or undefined. So that's what we just have to find those. Find the derivative, and that's it. Again, I'm not trying to make a big deal out of this, right? I'm not trying to make a big deal. You can take this derivative in your head if you want. It's fine. If you want to write it down, fine. So I want to find where this is 0 or undefined, right? Now notice this is a better form for this, because if I want to find the zeros, I want to know where a over b, a is 0. If I want to find where it's undefined, it's a over b, right? b equals 0. So again, while this is fine, this is, again, it's not that one form is better than the other. If I was going to take the second derivative, this is a better form. If I'm looking for zeros or undefined, this is a better form. So again, you should never look at these, they're algebraically equivalent, but you shouldn't look at it as one is right or one is wrong. They're just different forms, they have pro and con, right? One form is better for one application, a different version is better for a different application. So again, if I was taking the second derivative, I prefer this form. If I'm going to look for zeros and undefined, I prefer this form. That's all I'm doing. So I've just put the steps in here. Again, I'm not trying to make it a amount. I put in all the steps so you can check. I have a over b, right? 2 is not equal to 0, so I can divide through by 2, right? In other words, or you can think of it as a times b equals 0. This is not 0, so this has to be 0, right? Either way you want to think about it, they're the same. Again, here I have a over b. If I want a 0, a has to be 0. When you write x to the 1/3, again, you can look at the crib sheet. If you want to write, when you write a fractional power, again, you maybe forget this, but what this means by definition, is this. Right? So there's really not x 1/3, you're really solving this problem, right? So 1 cubed, of course, is 1, so I say x equals 1. Again, if you're weak with the algebra, this is your chance to look into it, really. I mean, the problem with algebra is you look at it as a very theoretical idea. I'm just learning these rules. Well, you're applying these rules. This is why I need those algebraic tools, right? This is why I need these algebraic tools. And again, there are not 1,000 of these rules. There's only a few that come up all the time. A times b equals 0, a over b, these come up all the time. And rules like this come up sometimes, right? So just pick them up as you go. Don't run away from it. You're not going to get stronger with algebra by simply ignoring it. But, you know, in a case like this, you're not just doing it for it affects the problem, right? It solves a problem. Anyhow, this is my 0. Now, where is the function undefined? Well, again, it's undefined. A over b is 0, right? A over b is 0. You can put the 2 in the top or whatever. Right, 2 on the top. A is this, B is this, so it's 0 where the bottom is 0. And again, to the 3rd power, right? So you can just look through that and make sure you're clear. But it's A over B, B is 0 is undefined. So again, I know where the critical numbers are, right? Where the function is 0, or here it's 0, or where I'm undefined. These are my critical numbers, this one and this one. And of course, they have y values as well. But 0 has a y value, right? And I need that because they give me my critical points. Again, critical points. The maximum is going to occur at a critical point or the endpoints, right? Understand that. The global optimization theorem says it's going to occur at a critical point or at the endpoints. So, right, I have the function is continuous everywhere, right? It's an exponential. And it's differentiable everywhere except where the derivative doesn't exist. I mean, you don't maybe have to be this particular about it. It's continuous everywhere and it's differentiable everywhere it's defined. I mean, I mean, again, you should think that, right? If you apply this and this isn't true, this is why you have problems. And you say, well, that problem's a gimmick or an exception or something crazy. That's not true. You should train yourself to think what is necessary, right? This is the error protocol in your code. When you input into your class, do you check that the function is in fact meet the criteria? You need to know that. So it's going to, the optimization, the maximum and minimum is going to occur either at the endpoints here, right? The endpoints, x is minus 1, or 3, right? The endpoints, or the critical points. You just make a table. I mean, it's that simple. Just simply make a table. Figure out the values of the function at the critical numbers, and just pick the biggest. The biggest one's the maximum. The smallest one's, I didn't ask for that, it's the minimum. And that's it. You're done. So the maximum occurs at the critical number, x equals 0, and the maximum value is y equals 0. Done. I mean, done. I mean, it's not that hard. And if we were to look at the picture, you see this is exactly what we have. Again, and for one variable, you can draw the graph easy, and you can maybe argue for two, you can draw the graph. You obviously can in higher dimensions and so forth and so on. So again, this is just testing. It sets up the procedure. So you can see there's no tangent line here, and that's the caveat, right? The derivative isn't 0 here, but maximums can occur where the derivative is undefined, right? You don't have a derivative. You can see from this side what would be the slope of the tangent lines from the secant lines, right? If you look at the limit of the slope of the secant lines, it would be up this way. If you come from this side, the slope of the secant lines would go up this way, right? So there's no derivative at this point, but yet a maximum occurs. So that's the maximum, and you see the minimum would be over here on the end. I didn't ask for that, but that's where it would be. So that's all we have. I mean, that's all you have. Now, the beauty of this is this extends to, what you'll do in Calc 3, to multiple dimensions. So think about having a box, right? A box, 0 to 1, 0 to 1, and the x, 0 to 1 on the y. How would you apply this to a box, right? Pause a second and think how you would do that. I mean, again, understand the power, where this goes. How would you apply this to a box? 0 to 1 on the x, 0 to 1 on the y. So this is what you're going to do in Calc 3. Pause the video and see if you can think about how you would generalize this. And you can do this. Okay, so pause a second and think about that. Okay, so if you had a box, what would you do? You'd know the maximum or minimum occurs either in the interior of the box. So you'd look for basically the critical points. You wouldn't have a tangent line in the interior, you'd have a tangent plane, and you'll talk about that in Calc 3, but so what? You'll look for the critical points in the interior, or the maximum or minimum is going to occur on the walls, right? On the walls of the box. Well, now you look at the walls of the box. How do you analyze the maximum or minimum on the walls of the box? Well, the walls of the box are the one-dimensional case that we're doing. You look at the endpoints of the walls or the interior of the wall, right? The middle of the wall. And so you apply this theorem now to the walls. And you'd do 4 problems on the 4 walls. So you'd look at the interior, and then you'd look at 4 problems on the 4 walls. Now, if you looked at a box in 3D, you'd look at the interior of the 3-dimensional, say, cube, and then you'd look at the 2-dimensional walls, so there'd be what? 1, 2, 6, right? And then on each of those walls, you'd look at the interior of the wall and the endpoint, and you keep breaking it down. But it works. I mean, it does work. This is how it's done. Another way you can generalize this is, again, you think there's all these tricks. Suppose I go from 0 to infinity, right? Let's, unbounded, outer space, 0 to positive infinity. How would you do it? Well, you go from 0 to 10, 0 to 100. So you go to 0 to 10, that's test case 1, you get a maximum. 0 to 100, test case 2, you get a maximum. 0 to 1,000, 0 to 10,000, 0 to 100. You see there's a pattern. For each of those approximation domains, right, 0 to 10, 0 to 100, 0 to 1,000, 0 to 10,000, you get a maximum. That's a limit, right? For your first, n equals 1, you have a maximum, 0 to 10. N equals 2, you have a maximum, 0 to 100. N equals 3, 0 to 1,000. N equals 4, 0 to 100, right? That's a limit. This is how you do it in practice. This tool is easy to use. This is how you do it in practice. So again, if you're an engineer or a scientist, you're working on a problem. So you say, I'm going to take a approximation domain. I have to limit it. I can't go to infinity. I went to 0, my domain 0 to 10,000. I ask you, why is 10,000 enough? Well, because I did tests. 0 to 100, 0 to 1,000, 0 to 10,000, 0 to 100,000. And because it's a limiting problem, I know it doesn't get any bigger, or that the changes at that point are so small it's good enough. You don't just say, I went from 0 to 1,000 because somebody told me to, right? Again, this is, you have to understand calculus if you are going to be good. You have to understand the math if you're going to be good. Now, I'm not saying you have to get into the ideas where you have to know how to do the limit and figure this out. That's what the mathematician on the team will do if they need to do it. But you should understand and feel it, right? Calculus isn't about taking all these derivatives. No one cares. Calculus is about global optimization. Calculus is about fundamental theorem of calculus. This is what calculus is really about. Not the pain and suffering you go through memorizing a bunch of gimmicks and tricks, right? That's nonsense. This is the calculus. Okay, the next thing I want to do is we want to look at a word problem, right? We want to turn an optimization problem into a word problem. And people think, again, it's hard because it's a word problem. Again, yes, but this is more realistic, and it's just about pulling the information out of the word problem. Now, on the exam, you're going to probably have an optimization problem in this form. Just calm down. Just go through the steps, and it should be fine. Okay, so here's a typical case. It's an artificial problem. A farm has 20 meters of fence that can be used to construct a rectangular pen. What are the dimensions of the pen if we wish to maximize the enclosed area? Again, it's a very artificial problem, but again, it meets all the criteria. Again, it's useful to draw a picture. Draw a picture, right? Draw a picture. As always, what information do you have? Right? Again, we did related rates were an application. Optimization is an application. Well, I know the area of the pen. I know that, right? I want to maximize. What are the dimensions of the pen which maximize the enclosed area? I want the area of the pen. They tell me the farm is 20 meters of fence. So the perimeter, right, I identify my variables. The perimeter is going to be 20. And if I want to call it, X and Y, length and width, whatever, it doesn't matter. I don't want these things to be negative. You're not going to have a negative length to the pen or width. Now, technically, you might say X should be greater than 0, Y should be greater than 0. But, okay, my tool is going to be closed and bounded intervals, so you'll see why this plays out. Right, I want greater than equal instead of just greater. All right, so let's take a look at this. What I want is the constraint equation. And again, this is always going to work this way. You know this is constraint optimization. You can do unconstrained, but that's for a different idea. Constrained equation, you're going to have a constraint, right? Well, where do you think the constraint comes from? What limits what you're doing? I'm thinking the 20, right? That's my constraint. You might have a certain amount of money you can spend. You may have, whatever, limited resources. Something usually constrains the problem. For me, it's the length of the pen. So write an equation for that. That's my constraint, right? Constraint, okay, technically constrains the freedom of movement of the variables, right? Sometimes they just give it to you, right? But it's going to constrain the problem. Usually you have to drive it, but some problems they just give it to you. It's basically going to constrain the variables. It's going to constrain these. So for me, the perimeter, right? Look at the perimeter is 2x, bottom, top, and the sides. And that's 20. So I want to write an equation using, it has to be, I need a constraint on the variables. And this is it. Again, it's probably not a bad idea I got a little sloppy here. I probably should put the units in here, right? It's meters. Again, the problem is, you might have problems where they give you, it costs, the fence maybe costs $20 per meter. So, but your constraint is meters, right? So you have to match up the units. All the units have to be the correct unit. That's one of the places people make mistakes on these problems. Remember, you need a constraint equation. And really, from all the problems, again, you shouldn't be spending hours on this. These equations are usually fairly straightforward. It's just, again, just use common sense and you can probably get these. All right, so just divide by 2. That's my constraint. Notice it constrains the movement of the variables. Right, but it comes about because this is a limit on my resources. Right, again, this matters. This is the kind of thing we do. All right, so once I have the constraint equation, and again, you will see this in other classes, right? You'll see this. This is not just unique a calculus pain exercise. So I have a constraint. Now what I need is what's called the objective equation. The objective equation is the equation you want to maximize or minimize, right? So in this case, what do I want to maximize or minimize? The area. So I need an equation involving the area, and then I'll turn it into a function. So again, what is it? It's area, x times y. I mean, it's not, you may have to look up the equation, write circular cone. Who knows, right? But you may, need to look it up, but it's usually something pretty straightforward. Don't make a mountain out of it, right? It's just look at it. If you're spending an hour on it, you're wasting your time. All right, but I need a function, right? I need a function. Calculus is about functions. And this is Calc 1, so it's function of a single variable. So again, how am I going to get this to a single variable, and what's that going to be for a function? Notice with the chain rule, and related rates, we had the same thing, right? We used the linking equation if we had too many variables. Here, that job is the same as what we have with the constraint equation, right? We need a function. So this is an equation. We need a function of a single variable. So I'm going to call that function, and the function will be either variable x or y. And right, so I'm just going to substitute in the objective equation. So I really haven't done anything. I'm just going to say a is a function of x. Notice I can't write f of x equals a equals xy. This is saying, again, this is saying f is a function of x. If you just said f of x equals a equals xy, it doesn't make sense. Again, you're not saying you're going to lose points for this. What I'm saying is you should be literate. You should be able to speak the language. If you come and work for me, or I interview and I talk to you about a problem, again, you're not literate in the field. You're not educated. You don't know how to speak properly. You can't communicate your ideas. So again, I'm not saying to panic about this, oh, you're going to lose 50 points on the exam. Not at all, but you should learn to be able to speak the language. This is saying I'm taking the function of x, and that value is area. So area is my y value, right? Generally, f of x equals y. Here I have a equals xy. They're my length and width and height. Right? Length and width, or width and height, whatever you want to call it. Now, again, how am I going to get rid of one of these variables? Always the constraint equation. The constraint equation. Because the constraint equation is if I take something from y, I have to put it into the x. If I take something from x, I have to put it into the y. Right? It's a zero-sum game. This is the constraint on my resources. So you can always do this. Always you can do this. So from the constraint equation, I'm going to remove the y. And now notice, this is now only x's. And so I have my function. I'd simplify, right? I distribute it. The reason I distribute it is because we're going to wind up taking the derivative. This is better for that than this. This is better for zeros. Right? So I'm going to distribute, and so that's my function now. Right? This is my function rule. Right? Because f of x equals a. Again, you could do the same thing. Y could be your variable, but it's a function of one variable. Now, again, I need, if I'm going to use the global optimization theorem, I need the function on a closed and bounded interval, right? I need the domain to be a closed and bounded interval. This, of course, is defined everywhere, but that doesn't help because the maximum min could be on the ends. So I need a closed and bounded interval, right? I need the domain to go from the bottom to the top, and I need to include the endpoints. Well, again, just look at the information you have, right? In the first step, I know that this is true. So x greater than or equal to 0 is good. That gives me the bottom. And again, now I need a top. Well, where is that going to come from? They give me y. But again, that's what the constraint equation does. It can convert y's into x's, right? The constraint equation, right, limits your freedom of movement. So it converts, right? I can change y's and x's and go between the two. So notice, if y is greater than 0, well, that says 10 minus x is greater than or equal to 0. And again, it'll always work. All your problems will work like this. It's not like this is a mystery. This is an algorithm that works for everything. right? Why is an algorithm good? It focuses your attention on what you need. You're not wasting your time on every problem as some, again, kind of mystic, enlightening experience. No, you know exactly what you're doing. Look at the constraint equation. Stop wasting time. So here it is. X is less than or equal to 10. That gives me the bottom. That gives me the top. I mean, this is it. So there you have it. And again, don't spend an hour on a problem. The worst thing you're going to see is you're not going to see it, right? Don't spend 5 minutes. See if you can get it. Test yourself. If you can't, then contact us. I mean, it's not that big a deal. Well, I mean, it is. I'm not trying to trivialize it. You have to do it. But I'm saying don't spend 10 hours, I guess is what I'm saying when I say not a big deal. Don't spend 10 hours. You're wasting your time. I guess that's really what I'm saying. Anyway, of course, it's a big deal when you don't know it. You got to figure it out. Here's my rule. Again, that's a polynomial. It's going to be continuous and differentiable everywhere. Notice I have my domain. It's bounded. I go from 0 to 10. It's closed and bounded. And of course, the range is already is a real number. Okay, so now again, notice what we've done. We've taken a physical problem, a word problem. Okay, a word problem. A problem from the world, a real world problem. Now you're impressed. And this is what you do. And I've converted this problem into a purely mathematical model, right? I'm not interested in your gut feeling or your opinion of what's happening. We've converted that real world application into a purely mathematical problem. Now you give it to the mathematician, or you can solve it yourself. Again, this is global optimization is a standard theorem. You do it all the time. So, I mean, again, at this point, it's a purely mathematical model, right? Purely mathematical model. So, okay, you just solve it using the technique we just developed. It's a purely mathematical model. Again, it's always the same. You don't need to reinvent the wheel. And in higher dimensions, Calc 3, you'll do the same thing. How did we do it before? I want to find the critical numbers. How do I do that? I find the derivative, right? Take the derivative. And again, I'm not making a mountain out of this. That's pretty straightforward. Find out where the derivative is 0, right? The zeros of the derivative, or where the derivative equals 0. I don't know. What else would you call it? 0. Factor it. Again, I'm not trying to make a big deal. Just factor it. Where is it undefined? Well, polynomial. It's defined everywhere. A over b. In this case, actually, b is 1 if you want to do it. Right? It's defined everywhere. So the critical numbers are, by definition, x equals 5. That's where it's 0. By definition. Again, not because I say so, or some stand on your left foot, face the east, and chant your mantra. By definition. By definition. So what's the next step? Make a table. Right? Notice I'm continuous everywhere on the closed and bounded interval, and I'm differentiable in the interior. Again, you should train yourself. Get into the habit of checking your constraints, right? So why did it not work for this problem? No, it's not a gimmick. If you have checked your constraints, you'd see that result doesn't apply. You need a different one, or you need to reformulate the problem. So meet the conditions of the global optimization theorem on closed and bounded intervals. Here are my endpoints. Here's my critical point. Evaluate the function. The largest is the max. The smallest is the minimum. So the max occurs when this x is 5 and the maximum area is 25. Okay, but we have x's and y's, right? You have to tell me the dimensions of the pen because I'm building it. I have to build it. So you tell me x is 5 is great, and then the technician comes to me and says, well, what's y? And you say, figure it out. No. I had a guy call me once, well, you're a mathematician. Can you convert, he's on a construction site, can you convert meters to feet? You can do it, I'm not here to do that. Anyway, x is 5. So if I want to relate x to y, constraint equation, right? Constraint equation. So y is 5. And again, it will always work like this. So in some of the homework problems, you're just going to do they're just going to give you the equation, the function definition and the domain, and then you do it. Some of the problems are going to be word problems. Again, on the exam, you're going to have optimization theorem. You're probably going to have a word problem, to be honest, because it's everything. But again, don't go crazy. The only thing is the objective equation, the constraint equation. Just try to step back, not panic, and use common sense. Try the homework problems again. We're not going to have time in the class to work out these problems. We just don't have enough. We're not going to have time in the labs to work out these problems. So you're on your own with this. So again, I encourage you, try some of these problems. You'll find they're really not that difficult at all. Certainly the ones that aren't word problems should be straightforward, right? If they're taking you more than a few minutes, you're just wasting your time, right? Be quick and efficient, get them done, and do what you want with your life. The word problems, if you're getting stuck on the equations, that can happen. Again, it can happen, but don't waste hours on it. If you're stuck, right, just talk to us and we'll get it for it. Help you see. But look for common sense ideas. Just to step back, you look for common sense ideas. All right, so I think that's pretty much it for optimization. Oh, wow, here, depends should be axis 5 last one. That's the area.